Hi, my name is Nikos Nikolov. I am 19 years old. I'm studying currently at the Maastricht University. I'm studying computer science, the bachelor degree. And here is a video to showcase what I did during March 2026. This is a prototype for fire detection and early prevention of fire occurrences in vicinities that we want to observe. So here, let me kickstart very quickly with a presentation. This one utilizes IoT mechanisms like sensors and machine learning for preventive purposes. So first of all, let's discuss what's the problem with fire prediction at the moment. So we have people trying to use systems that have individual characteristics such as smoke or temperature, and this is more of a generic mechanism that is used for prediction instead of something specific for specific environmental conditions. So the fire preventer and detector I'm presenting is going to use machine learning to analyze patterns and predict fire occurrences in real time. Here are some applications we could have, like forest, historic buildings, facilities, and malls in general. We could see lots of applications outside of the spectrum, and they involve things that we want to protect and they are of great importance to us. So starting off, we would begin with the dispersion of millions of IoT sensors to so many areas around us, areas that we want to track for their conditions every day, every time, every minute. So this will be tiny wireless and noise-free sensors. They will be handled remotely. There will be a private API that gets connected the data from the sensors to our system, to our databases, and we will be using this data for processing, analysis, and prediction purposes. So the idea is to have a very early prevention mechanism that will be trained based on this data. So establishment will be on lots of areas. We can imagine things from forests all the way to electrical panels inside buildings, so that we can have a very broad picture of what's happening in the vicinity we're trying to track. And main sensors we could use are humidity, temperature, and carbon emissions. This is a very general presentation. We could have a lot more niche and specific sensors we're going to take advantage of. And so the cycle of fire prediction starts with the data. So we have the IoT data, things that are real, things that are coming from our sensors, and we have the synthetic data. Synthetic data will be created by us. So the IoT data have a problem. They're biased in favor of non-fire, and this is because most times we won't have fire. So most of the data logs will be of non-fire events, while the synthetic data will come into the game to discuss the idea of what happens when we have fire, and we'll add some noise. This goes through the data processor and the AI algorithm that produces a result for fire and non-fire. That will be a probabilistic prediction. So some of the machine learning models we're trying to use, and we've already made a lot of code about it, are regression, tree-based, gradient boosting, and vector models. Here's a picture of how they should work. Here's a neural network as well. That was the idea previously, but we are thinking maybe we should, maybe we shouldn't use it. The reason is a neural network is very expensive in terms of processing power, so we want to avoid that. The orchestration mechanism has to do with data coming from sensors to the central management system, and then going to the AI backend, and the backend sends back to the server what the prediction is, and then the prediction goes to the dashboard. So the dashboard is the final thing someone can look at and like understand what happens in their tracked vicinity. And so for the realistic data collection, as we said, of course we cannot get to cause intentional fire into a forest. This would be criminal. So we're not doing that. But what we're doing instead is to represent fire events with synthetic data. And the synthetic data will be created based on possible ranges of the sensors. This is given by the company that produces the sensors, plus academic and non-academic work that has been done up to now and relates to what is the image that we have before fire occurs. And we will add on that realistic data, actual data. This comes through a common processing unit, and this formulates a holistic data set with all conditions covered. And here are a few screens that have been designed to showcase how the final dashboard will look like. This is more or less a generic picture. It's for some metrics that we might have, like humidity, temperature, air quality, and fire probability. And there is also a graph on the right hand side to support the metrics that the system has received and indicate when there is more danger compared to what we should have. And this is me. As I explained myself before, I like working with AI and machine learning, basically incorporating things into software. And also I'm interested in agent technologies, so how we can inject some agentic AI into actual software and support users by eradicating the most routine and most boring tasks from them, so that the robots can do them. So in addition to that, you're going to be given a report that is supplementary, so you can have a look at it. It has a bit more details. It's mostly about data and machine learning. And here is the prediction dashboard. Here's a prototype. So what I'm going to do is upload a file. This connects real time to our machine learning backend. So we will see predictions right now. The test CSV file has data that the models never ever had access to. So they do not know what these data are. So they cannot make safe predictions. They have to predict as if they're actual data, as if they're getting into the play during an actual scenario. So we're gonna have some samples here. I'm gonna randomly pick, for instance, sample 15, and I'm gonna make a prediction for it, and we can see there is a result board here. It says prediction 0, meaning it's not a fire. This one does not indicate a fire. And probability of non-fire is 0.999. It's very high, very certain about it. Probability of fire is something very minimal, and we also see that it's a correct prediction. And we can also test a few more of them. Here it was the opposite one, so the prediction was 1, meaning there was fire actually, with similar probability certainty. And one more, similar to this. So most of the times we see these percentages. Most of the times you'll see more than 90%, meaning that the system is very certain about the prediction. On top of that, I want to explain a little bit what the data look like. So I'm going to go to the train or the test. They are very similar. So what you can see is first line are the features. So for instance, temperature, rate of rise for the temperature, carbon emissions, and things like that. And every next line represents one sample. So we can see the respective values separated by the commas. And so the last one represents if there is fire or if there is no fire. Again, let me remind you, 0 is for non-fire, 1 is for fire. So we're taking that into account, we're getting that into the system and using the features of each line. So sample 1 corresponds to the first line of actual data. It makes a prediction of whether there is fire or not. And so because of this prediction, we can check whether it's correct because we're also giving it the correct result, but the models do not take it into account. So they are very independent of that. So here's all I wanted to talk about, and thank you very much.